Hello everyone, welcome to week 12 problem solving sessions of the course on regression analysis. I am Shreya, one of the TAs for this course, and today we'll be discussing problems based on um, week 12 lectures. So let's get started. Okay, so before moving on, I would just like to touch up on whatever we've learned so far and then proceed to the other things. Okay, I hope I'm audible. So, up until now, we have learned about uh, OLS, ordinary least squares, how to fit them, what are the Gauss-Markov rules or assumptions, and what to do if there is a violation of those assumptions, and then how to correct for that. How do you transform data to when the response variables are not of, the error terms when they are assumed not to follow a normal distribution, and what are the things that we do. So first things first, we learned how to fit an OLS, and then which is nothing but ordinary least squares. Okay, the assumptions, how to get the distributions of betas. We learned about hypothesis testing of the parameters, and then we learned about something about generalized least squares. Okay, and what did we have here? Here, if we had a response variable y equal to x beta plus epsilon, and in case of an OLS, we had that variance of epsilon would be equal to sigma square I. Then only the homoscedasticity assumption would hold. Okay, but in case of generalized least squares or GLS, what we had was variance of epsilon equal to sigma square into V. Now V could have different elements like V11, V22, okay, VNN, V12, V1N, something like this. So this would arise if error variances were unequal, or for the case if the y's were correlated. Okay, and in because of which we would have such off diagonal elements. Okay, so what were the problems in estimating or in getting the GLS function? So the problems were that the ordinary least squares estimate, which was x prime, x inverse, x prime y, this was not, and it was not the best linear unbiased estimator or blue. Okay, so this was the case where we learnt about generalized least squares. Okay, and then what did we do? We made some transformation to this model such that the beta hat GLS was nothing but x prime v inverse x whole inverse into x prime v inverse y. Okay, and we also learned that the weighted least squares was a special case of generalized least squares. Okay, in the sense that in V it was denoted by W and we had only these things. Okay, okay, and these were 0 and the estimate was beta hat GLS or weighted least squares was nothing but X transpose W X inverse X transpose W Y. Okay, where W is nothing but 1 by 1 W11, 1 by W22 and 1 by WNN. Okay, and all these off diagonals are 0. Is it alright? Okay, so we learned about this. And then this is how we fit a generalized least squares. But even here, the assumption was epsilons, they follow some normal, let's say 0 and sigma square v. So the distribution remained normal. Now the question is, what happens if errors are not normally distributed? Okay, this is the case which is typically solved by GLM or generalized linear models. Okay, this one was generalized least squares and this is actually generalized linear model. Okay, just excuse me for 2 minutes. Sorry about the disturbance. Alright, so where were we? Yes, we were learning what to do if errors are not normally distributed. Okay, alright. So herein comes the role of generalized linear models. Okay, and now how does this differ from generalized linear models? So in case where error variables are not normally distributed, or in case where if we construct a vector of nonlinear functions of the response, that is, if we transform y to eta y, where eta is nonlinear, then we would get a vector like this: eta y1, eta yn. Okay, then if we have something like expectation of eta y equal to x beta, that is also the case where we can apply GLM, and these are and or situations. Alright, okay. So far we have assumed errors to be normally distributed. Now the advantage in assuming that, let's say some mu or sigma square I. So here we have seen, if we plot an ordinary least square, we have seen that expectation of y is actually equal to x beta. Okay, but in case of GLM, we'll have expectation of eta y equal to x beta, where eta is some nonlinear function. Okay, now how to find eta? This is the next question. So to do this, we'll take help of a family of distributions which is known as exponential family of distributions. Okay, so for the sake of simplicity, here we are considering one parameter exponential family of distributions. Alright, now how do we characterize an exponential family of distributions? So let's say that u1, u2, un is a random vector, okay, is a random variable, u is a random variable, and this is a random vector. Okay, if we have something like this, let's say each ui is drawn IID from some distribution. Okay, let's say some distribution D. Okay, now if we can write if u theta, and let's say this distribution D theta is the population parameter of interest. Okay, now if we can write this PDF or PMF as SU T theta into e to the power AU d theta. Okay, or if we take exponential in front, then this would be ln SU plus ln d theta plus AU into d theta. Okay, or if we rearrange it, we can write it as AU d theta plus DU plus C theta. Okay, where DU is equal to ln SU and C theta equal to ln T theta. Okay. If we can decompose the distribution of D into this form, okay, such that AU will be a U containing term, B theta will be a term containing theta, which is a parameter of interest. Okay, du will also be a quantity which is only dependent on the observations, and c theta will also be a function which is solely dependent on the parameter of interest. Okay, now note that apart from theta, we could also have so apart from theta, if we have other parameters, then those are actually nuisance parameters. Okay, so we are good to go with this thing despite the presence of nuisance parameters, given that the nuisance parameters are, let's say, known to us and it's not the parameter of interest. Okay, so this is how we treat it. So let's say within this b theta we could have something else also, let's say b theta phi or something. Okay, so those are actually my nuisance parameter, which is not the parameter of interest, and uh, those can also get incorporated into b theta and c theta, but it should not get incorporated into AU or DU. Alright, now if we see that AU equal to U, we say that the distribution is in its canonical form. What is in canonical form? The distribution is in canonical form. Okay, and another important thing that we have learned is that this parameter b theta is actually the natural parameter. Okay, so in cases where some nuisance parameter is incorporated into b theta, Then we have to see if that parameter is actually known, then we'll just take the terms, or we'll sort of ignore those other terms if possible. Okay. So as we've seen in the example of a normal distribution, that the natural parameter is mu by sigma square. Okay. So b theta is mu by sigma square, but uh, while fitting models, we have taken the form of natural parameter as mu. Okay, this is what I'm referring to over here. Alright, but we will come to that later. But first things first, this is if AU equals to U, then we say distribution is in its canonical form and B theta is said to be its natural parameter. Okay, and any other parameter apart from theta is actually a Nuisance parameter. Okay, for example, let's say normal mu sigma square. So sigma square in that case is not of interest, and so that is nuisance. Okay, let's say binomial NP. Okay, usually P is of interest. Okay, in that case N is usually nuisance. Alright, now we also learned about some family of distributions. So one parameter exponential family of distributions. Okay, so we learned who belong to this family. We learned that binomial NP belongs to this family. We learned that Poisson NP belongs to this family. Okay, we learned two other continuous distributions. So these were actually discrete examples of discrete distributions, and gamma and exponential were examples of continuous distributions. Okay, so just to reiterate, there are these are not the only functions which belong to this one parameter, sorry, exponential family of distributions. There are several others. Okay, and how to check? We'll match it with the this equation or this form, which is here. Okay, so if we see that f of u theta equal to e to the power au b theta plus c theta plus du, if this holds with the conditions, then we say that this belongs to a one parameter exponential family of distributions. Okay, all right. So giving you an example of, let's say, binomial NP. What is the like you how is the probability mass function written? It's written as NCU p to the power u 1 minus p to the power n minus u. So we can write this as NCU p to the p by 1 minus p whole to the power u into 1 minus p whole to the power n. So this one we can write as exponential ln, this thing, NCU p by 1 minus p to the power u to 1 minus p whole to the power n. So this we can write as exponential ln NCU plus u ln p by 1 minus p plus n ln 1 minus p. Okay, so now matching it up, we see that AU is actually u, B theta, so here parameter of interest theta is p. Okay, so B theta here is actually accompanied by this thing. So this is ln p by 1 minus p. Got it? Now C theta is actually n ln p 1 minus p, and du is nCu. So you see, this nuisance parameter n could be a part of both C theta and du. But since this is not our parameter of interest, we'll kind of ignore it. Alright, so binomial is one example where the nuisance parameter is embedded into both C theta and du. Alright, so given this, next we learned about Poisson distribution. Okay, the Poisson distribution, yes. So Poisson distribution, the PDF is PMF is, sorry, e to the power minus lambda, lambda to the power u by u factorial, where u could be 0, or u could be 0, 1, 2, and so on. Okay, here u could be 0 or 1. Alright, so this is how FU looks like. Now we can write it as exponential ln e to the power minus lambda, lambda u by u factorial. Alright, so this is actually exponential ln e to the power minus lambda plus ln lambda to the power u minus ln u factorial. So this we can write as exponential minus lambda plus u ln lambda minus ln u factorial. So if we match it, then we see that AU is actually equal to u. B theta or lambda, here theta is actually lambda, which is the parameter of interest. So B theta is actually ln lambda. C theta is minus lambda and du is actually ln u factorial. Alright, so as in case of binomial, here au equal to u, this is the distribution is actually in canonical form. Similarly here, this Poisson distribution is also in its canonical form. And ln lambda is actually its natural parameter. And for binomial, ln p by 1 minus p was its natural parameter. Alright, going back to examples, if we considered gamma, then we would have had the distribution as if u alpha equal to theta to the power alpha u to the power alpha minus 1 e to the power minus u theta u by gamma alpha. Okay, so if theta is the parameter of interest, we can write this as exponential ln theta to the power alpha u to the power alpha minus 1 to the power minus theta u by this thing. This is actually equal to exponential of L alpha ln theta plus alpha minus 1 ln u minus theta u minus ln 1 by this thing. Alright, so here if we have au, that will be u. Okay, b theta would be actually equal to minus theta, du will be equal to alpha minus 1 ln u, and c theta should be alpha ln theta. So here again this Newton's parameter alpha is incorporated into both c theta and du. Okay, or we can include this thing in any one. So alpha ln theta minus ln 1 by gamma alpha. Let's say. Alright. So this is also an example of this would be minus ln gamma alpha because it's already minus. Yes. Okay. So this will be alpha ln theta minus ln gamma alpha. Alright. Now if let's say this gamma distribution is parameterized as this thing, f of u alpha equal to 1 by theta to the power alpha gamma alpha u to the power alpha minus 1 e to the power minus theta by u. Sorry, minus u by theta. Okay. In that case, we would have exponential ln, this entire thing, we would have u to the power alpha minus 1 e to the power minus u by theta to the power alpha gamma alpha. So then we would have exponential alpha minus 1 ln u minus u by theta minus alpha ln theta minus ln gamma alpha. In this case, AU would be U. Okay, so it's canonical, yes, but B theta is actually 1 by theta. So this is the inverse function. Alright, so be very careful as to how this function, be it gamma or be it exponential, how they are constructed. Okay, accordingly, b theta is going to change. If you are given this form of the equation, and then if you say b theta equal to theta, then you are wrong. So look carefully into how this distribution looks like, and then try to derive it from the first principles. Okay, instead of blindly following what is written in textbooks or classrooms. Alright, so same with exponential. Okay, if you have something like this exponential theta e to the power minus theta u, so this would be ln e to the power theta e to the, sorry, ln ln, sorry, it would be e to the power ln theta e to the power minus theta u. So this would be e ln theta minus theta u. Okay, so in that case, AU equal to U, B theta equal to theta minus theta, C theta equal to ln theta, and DU equal to 1. But similarly, if we have 1 by theta e to the power minus u by theta, then this will come down to exponential minus ln theta minus u by theta. So in that case, b theta would become minus 1 by theta, and c theta would be minus ln theta, which is fine. Alright, so in cases of exponential and gamma, please be careful as to how the distribution is parameterized, and then accordingly you should follow. Also, we learned about something, that expectation of AU is actually C prime theta by beta theta. So we'll check it with binomial and Poisson. So in case of binomial, AU was U. Alright. So expectation of AU is actually expectation of U, which is nothing but NP1 minus P. Sorry, this is not expectation. The expectation is NP. We'll see if this is holding true with C prime and B theta. So C theta is how much for binomial? This is N ln 1 minus P. Okay, so this is N ln 1 minus P, and B theta is how much? This is ln P by 1 minus P. So C prime theta is actually N by 1 minus P. Okay, so this is C prime theta by B prime theta, and B prime theta is actually 1 by P by 1 minus P into P by 1 minus P, again we'll differentiate. So that would become beta theta is ln P by 1 minus P. So beta prime theta is 1 by P by 1 minus P into 1 minus P whole square. Then we'll have 1 minus P into dP minus P into ddP of this is minus 1. So this will be 1 by P into 1 minus P. So therefore C prime theta by B prime theta is actually N by 1 minus P by 1 by P into 1 minus P. So this is NP 1 minus P by 1 minus P. Cancelling, it is NP. Alright, and if we have to find out variance, let's say variance of AU This is actually b double prime theta, c prime theta minus c double prime theta, b prime theta by b prime theta whole cube. Okay, so b prime theta is 1 by p into 1 minus p. So b prime theta is 1 by p into 1 minus p. So b double prime theta will be p into 1 minus p whole square. Okay, and then 1 into ddp of p into 1 minus p minus p into 1 minus p into 0. Okay, so this will be ddp of p is 1 minus 2p by p into 1 minus p square. Alright, and c prime theta we have obtained as n by 1 minus p. Okay, c double prime theta is equal to 1 minus p square, 1 minus p into 0 minus n into ddp of 1 minus p, that is minus 1. So this is n by 1 minus p square. Okay, and b prime theta is this thing. So if we put everything together, this is actually b double prime theta 1 minus 2p by p into 1 minus p square into c prime theta is n by 1 minus p. Okay, minus c double prime theta is n by 1 minus p whole square into b prime theta, that is 1 by p into 1 minus p by b prime theta cube, that is 1 by p into 1 minus p cube, 1 minus p cube. Okay, so then what do we have over here? We have 1 minus 2 p n by p minus n by p by p cube. Okay, and then that would be equal to 1 minus 2p into n minus n into by p into p cube. So this would be p square. So here we would have 1 minus 2p into n minus n into p square. So it would be n minus 2pn minus n p square. Okay. All right. So this is there must have been some issues over here. Okay, so we'll fix this later. Okay. All right. So moving on, I'll give a little bit more clarification in the next session. So moving on, variance of AU is this. Expectation of AU is actually C prime beta by B prime beta. Let's say for Poisson, what do we have? For Poisson over here, we have B theta as ln lambda. So B theta for Poisson is ln lambda and C theta is lambda. So C theta is actually we can consider as lambda. Okay. So C prime theta by B prime theta is actually 1 by lambda, which is equal to lambda. Alright, so this is actually holding true. We'll talk about the variance part in the next class. Now that we have these and we know what is a canonical form and how everything is distributed, how do we actually fit a GLM? Okay, so what do we do is that we consider eta y, the eta as the natural, sorry, we consider b theta as the natural parameter, okay, and we take expectation of b theta equal to x beta and model this thing. Okay, for example, for binomial, we know that the natural parameter b theta is actually ln p by 1 minus p. So we model this as expectation of ln p by 1 minus p equal to x beta. Alright, so this is why natural parameter is very important and we should be able to do this. Okay. Okay. So this function which sort of links the natural parameter to this uh, equation is actually called as a link function. Alright. So when we were fitting normal equations, okay, so if expectation of yi equal to mu I, let's say, so g mu I we are fitting as xi prime beta. Okay. So in case of normal, g of mu I is equal to mu I, which is expectation of y. Okay. But in case of binomial, we have g of mu I equal to ln p by 1 minus p. Okay, so the important thing here is that we use some other this link function which is determined by the natural parameter, and then we fit that into our modeling, and then we obtain these estimates. Fine. So let us solve a few problems to get more clarity on this matter. Okay, so here we see a generalized linear model is used to deal with situation in which ordinary least square estimation is not blue, error variables are not normally distributed, or error variance are not constant. So here answer is option C, that error variances are not normally distributed. If variances are not constant, we could also fit GLS. Okay, and ordinary least square is not blue, that also holds for GLS. Okay, but GLM is used when error variables are non-normally distributed. Alright, moving on to question number 2. So this is a Weibull distribution, and the parameter of interest here is lambda. K is a nuisance parameter. So what is the natural parameter? First things, is it in canonical? Is it the first question is, does it belong to the exponential family of distributions? Okay, so then how will we check it? We'll write it as if x lambda is equal to exponential of ln k by lambda x by lambda to the power k minus 1 e to the power minus x by lambda whole to the power k if x is greater than or equal to 0. Okay, now this one we can write as exponential ln k minus ln lambda plus k minus 1 ln x by lambda minus x to the power k by lambda to the power k. Okay, So here what do we have? Here we have AU equal to x to the power k and d theta equal to minus 1 by lambda to the power k. Okay, and this thing c theta is equal to, we can write as ln k minus ln, uh, so I'll write it clearly in the next page. So if x given lambda equal to ln k minus ln lambda plus k minus 1 ln x minus k minus 1 ln lambda minus x to the power k by lambda to the power k. Okay, so AU is equal to x to the power k. V theta equal to minus 1 by lambda to the power k. C theta equal to minus ln lambda minus k minus 1 ln lambda. So this is actually minus k ln lambda. Okay, and d theta can be written as ln k plus k minus 1 ln x. Sorry, not d theta, du. Okay, so yes, the answer is yes, it is in one parameter exponential form. Okay, or I would not say one parameter over here because nuisance parameters are also here. So let's say it is in the, it belongs to exponential family. Alright, so now the question is, what is the canonical form? So this is actually its canonical form. That is this thing, option C. And now if somebody asks for the expectation of AU, so the first thing, is it canonical? The answer is no. Why? Because AU is equal to, U should be canonical by definition. Here we have AU equal to U to the power k. Okay, so this is not canonical. Okay, so expectation of U to the power k will be C prime theta by B prime theta. So this is not actually a canonical form, and if we want to use this evaluation technique, we can use this to obtain expectation of u to the power k. Alright, now moving on. Okay, this was the next question. Is this density in canonical form? So the question answer is no, because au equal to u to the power k. Okay, alright. Now the next thing is, which is the natural parameter? So natural parameter is actually this thing, it's repeated, minus 1 by lambda to the power k. Alright, so with that we have learned how to find out whether a distribution belongs to the uh, family of exponential distributions, and if so, then how to formulate the linear regression, I mean the generalized linear model. So if let's say we have Poisson, then we have the natural parameter as ln lambda, okay, or beta theta equal to ln theta, okay. So then the link function is actually a log link. Alright, so then if we have to write it like this, is g mu I equal to xi prime beta, then for a Poisson distribution, we write ln mu I equal to xi prime beta. Okay, so then in that case we'll write mu I equal to e to the power xi prime beta. Mu I is nothing but expectation of yi equal to e to the power xi prime beta. So then the model is yi equal to e to the power xi prime beta plus epsilon. Okay, so similarly for binomial we had mu I equal to ln p by 1 minus p. Okay, and we had that we had g mu I equal to xi prime beta. So g mu I was what? Ln p by 1 minus p equal to xi prime beta. Okay. So then we could write p I equals to e to the power xi prime beta by 1 plus e to the power xi prime beta. Okay, and pi, if I consider not exactly binomial, if I consider this to be Bernoulli, which is binomial 1p, then 1pi, then pi is actually expectation of yi. So if we have yi variables as binary variables 0 or 1, then yi would follow Bernoulli p, and then expectation of yi will be pi. Alright, fine. Now that we have learned about natural parameters and the canonical forms, now the next thing that we try to do is how to estimate betas. Okay, so how is it done? It is done with taking the help of the likelihood function. Okay, so what do we use? We use the method of MLE, or maximum likelihood estimation. Okay, so we use maximum likelihood estimation, and what do we do? Here we write down the likelihood L, and then usually what do? We maximize this function with respect to betas. Okay, now this usually is not straightforward, so we use iterative methods to do this. Okay, but first things first, how to write the likelihood? Okay, so likelihood is nothing but product of ui given theta. Okay, but it's mathematically it is formulated like this, but actually it is theta given x. So what we are trying to infer from likelihood is that given that we have some observations, what is the likelihood that theta will be equal to something or will belong to some range. Okay, so even though the functional form is similar, but there is an intrinsic difference between likelihood and density. Density, PMF, PDF, it's like given you have some population parameter of interest theta, what is the probability that you observe something, observe u's or x's. But likelihood is that we don't know about theta. Given that you have these observations, how likely is theta to take a certain value? Okay. Now moving on to write the likelihood function, we'll have to write it down as a product. So here we can write it as product of exponentials into ln, or I'll write a u b theta, a ui b theta plus c theta plus d ui. Okay, so since we have product of exponential, when it goes up it will become summation. So it is summation aui into b theta plus nc theta plus summation d of ui. All right. So then we will get our natural parameter from this b theta or b theta I, and then we'll fit we'll so b theta I would be some form of the xi prime beta. So we'll plug this value over here and then we'll differentiate with respect to beta. Okay, and this is usually done by numerical approaches like the iteratively reweighted least squares. Okay, or IRLS. So we'll use, so IRLS will give us the maximum likelihood estimator for betas. Okay, so you understand where the betas are getting incorporated. So let's say if we take an example of the Poisson distribution. Okay, u1, u2, un comes from Poisson lambda. Poisson lambda I, let's say I'm writing it for the purpose. Okay, so what was the model ln lambda I equal to xi prime beta. Okay, this is something that we had. So if I have to write f of ui given lambda I, this is actually, so L of lambda I given ui, this is this, so it will be e to the power minus lambda I to the power ui by ui factorial product I equal to 1 to n. Okay, so this can be written as product of exponential ln to the power minus lambda I to the power ui by ui factorial. We can write this as exponential of minus lambda I plus ui ln lambda I minus ln ui factorial and then product. So when this goes inside, this will become exponential summation of lambda I plus summation ui ln lambda I minus summation ln ui factorial. Okay, so here wherever we have ln lambda I, we are going to plug xi prime beta and then we are going to solve for. So lambda I in that case will be e to the power xi prime beta. So wherever we'll find lambda I, we are going to plug this value and then we'll get the likelihood, and then we have to differentiate this likelihood iteratively with respect to the betas, and that is how we can obtain estimates of GLM estimates of beta. Alright, so very quickly, if we have some distributions and we have to choose the link function, then if we have Poisson, we'll choose log link. If we have binomial, we'll choose logit link. Okay. So in case of Poisson, G mu I equal to ln mu. In case of binomial, G mu equal to ln mu by ln p by 1 minus p. Okay. In case of normal, we have G mu equal to mu. Okay. So this is the identity link. Okay. If we have, let's say, exponential, if the form is this, then we have G mu equal to 1 by mu, which is the inverse link. Okay, fine. So we learned about this, how to fit generalized, not generalized, linear models. We learned how to fit generalized linear models, how to estimate the parameters using the likelihood, and also we learned a little bit about nonlinear estimation. And I'll just briefly talk about it, but let me just put my computer is low on charge, so let me just do that. Okay, all right. So the next thing that we learned about was nonlinear models. Okay, so linear models were called linear because it was linear in parameters. Okay, but for nonlinear models, these are not linear in parameters. Okay, we also learned about something which is called intrinsically linear, which is this model where we can write it as y equal to e to the power theta 1 plus theta 2 t plus epsilon. So if we take ln y, then we have theta 1 plus theta 2 3 plus epsilon. So taking one transformation, if it makes it linear, then we say usually it is intrinsically linear. But what is an example of a nonlinear model? Let's say if we have y equal to something like theta 1 t by theta 1 minus theta 2 t, sorry, theta 1 t minus theta 2 t. Okay, or if we write it as uh, sorry, if we write it as y equal to theta 1 t by theta 2 plus t. Okay, so these models cannot be transformed and made linear just like that. Okay, so in that case as well, we could go for nonlinear estimation. So nonlinear estimation is essentially y equal to some function of the regressors t1, t2, tk, theta 1 to theta p plus epsilon. Okay, where t1 to tk are the set of regressors and theta 1 to theta p are the set of parameters. Okay, so we can write it this as expectation of y equal to f of t and theta, and if we assume that expectation of epsilon equal to 0 and variance of epsilon equal to sigma squared I, and then proceed, then this would be how we fit a nonlinear model. Okay, so if we want to find out the least squares, if we want to use the least squares technique, then also we use this thing, we use s theta equal to y minus f of t theta hat, or let's say this yi minus f t theta whole square summation I equal to 1 to n. Okay, so this will give the sum of squares due to residuals, and then we differentiate with respect to theta equated to 0, and then we get the normal equations, and then from there we can estimate theta hat. But this is not very easy to do. So we'll talk about nonlinear estimation more on the next class. Today, before ending the session, I want to show a few ways or how you can actually carry out this estimation using R software. Okay, so fitting GLM using R is what I would like to give a brief hands-on on. So let's just do that. Alright, so I am going to share the screen. Okay, so now, alright, so in order to use this, we'll use a function called GLM. Okay, so if we press F1 over here, then this is the documentation tab which will open. So this function comes with the default stats package. Okay, just whenever you are opening any documentation, the package name where this function is incorporated is usually given in second brackets over here. Alright, so it's by default this stats package is there in the model. So we need not uh, do a library stats, it will already be there. Now here we have to give a formula, we have to give the family and then some other parameters to give to get the fit. Okay, so let's say I have let's say tossing a coin, or let's say not tossing a coin, let's say that a person responding to a drug. Okay, so y equal to 1 if person I, so yi equal to 1 if person I is cured. Okay, and yi equal to 0 if person I is not cured. Okay, and let's say we want to check if y is depending on age or gender, age and gender. Okay, so let me just write 10 observations. So I'll write this y column as, let's say first person doesn't respond, second one doesn't respond. Okay, so this is a parameter of, so this is a vector of my observations. So y, how many will it have? If I run it, it has 10 values, numeric 1 to 10. So let me just enter the age of this person. Let's say age is 29, 34, 18, 15, 72, 56, 90, 58, 62, and 45. Okay, and so age is also a vector of length 10. And here again I am entering gender, let's say. Let the first person be male, second one also be male, third one is female, fourth one male, fifth, sixth, seventh, let them be females. Then we have male, then we have female, then we have male, then again we have male. So how many do we have? Okay, one more, so I'm going to, let's say, move one. Alright, so here I have this data set. Now I want to fit, since this is binary and I want to test this, my default, I should be fitting a GLM with family with binomial and a logit link. So LNP by 1 minus P is actually called logit link, logit P. Okay, so logit P is P by 1 minus P. So in order to do that, I can write here GLM and then the formula is Y on. Okay, so one more thing, since gender is a dummy variable, gender should be a dummy variable because it is categorical with two levels. So there should be one dummy variable corresponding to gender. Alright, so let us just find out how it is categorizing this thing. So GLM Y, I am going on age plus gender. Okay, family, I'm giving it as binomial and link equal to logit, and let me just output this one. So see, we have this coefficient estimates. Okay, so gender M means that it is already making the dummy. Alright, so if this is called a model and we give summary of model, then we find the estimates of beta, okay, and the standard errors, their z value and the p values, corresponding p values. Okay, so if this is the model ln p by 1 minus p equal to alpha plus a plus beta x, beta age plus c gender, then I am getting b and c. Okay, by this procedure. Now, if I want to use a Poisson, let's say, if I change the question a little bit, and if I want to count something, let's say number of accidents, all right, and this depends, let's say, on number of road repairs in last month. Okay, so this is my regressor then x. All right, and if I just take this example and change it into some count variables 2, 3, 1, 1, 5, 0, 0, 1, 0. Okay, And if this, let's say, is the number of repairs, this is accidents, this is repairs, let's say 2, 4, 8, 5, 2, 0, 0, 3, 2, 3, 1, something like this. Okay, so if this is the set and I want to fit a Poisson regression, all I'm going to do is I'm going to change family binomial to Poisson and link will become log, or we don't need to specify because it will automatically take it as a log link. Okay, similarly, if we have a very skewed and strictly positive distribution, let's say, and we hypothesize that this distribution is from exponential with inverse link. That is, PDF is 1 by theta into e to the power minus x by theta. Okay, if this is the thing, then sorry, it doesn't need to be extremely skewed, but it should be a strictly positive distribution nonetheless. So if we hypothesize that it should be exponential with inverse link, all we have to do is so here okay, so here it should have been accidents and then this should be on repairs. So this is how the model would look like. Alright. Then we were talking about strictly positive. So let's say y equal to, I'll add 1 to all of these. Okay. So if this is y1 and then x size remains same, let's say this thing, x1 equal to c, this thing, and I want to fit an exponential with inverse link, all I have to do is I have to write model GLM y1 on x1 family equal to exponential link equal to inverse. Okay. Okay, then we just have to find out how to fit an exponential GLM, but the the only change that we need to make here is this thing. So let me just try with gamma once. Okay. If I give gamma link equal to inverse, then here is the estimate. Okay. So if I do have a highly skewed and strictly positive distribution, I could hypothesize that it is a gamma distribution with inverse link. Okay. And then we'll have, we can fit the model as this: GLM family equal to gamma and link equal to inverse, and this will give us a summary of the thing. Alright, so with that, I'll end today's session. Thank you so much for listening, and I'll see you in the next class.